Hey guys, Dr. Cadell here, and this is the spectroscopy experiment. So the idea today in this experiment is that we want to determine the concentration of two different ions in an unknown solution. The two ions are going to be cobalt-2 and copper-2. In order to do that, we're going to use a technique that's really common and valuable in chemistry, which we actually have seen before in the mass percent sodium chloride experiment. So we're going to use a standard curve. The idea is we pick a variable, it's been picked for you, that depends linearly upon the concentration of the ions. It ends up that the absorbance of light by an ion is linearly related to the concentration in that solution. So the basic idea is we're going to use an instrument called a spectrometer that shines the light through our sample, and it rotates through different wavelengths between 400 and 900 nanometers at first. And it knows the intensity of that light before it hits the solution, and it measures the intensity after. And from that, it's able to calculate the absorbance, how much of that light was absorbed by the solution. And that's the dependent property. That's what depends linearly upon how much of the ion there is in there. So that's the big picture of how we're going to do this. So as with standard curves, we are going to generate our standard curve by making up solutions whose concentration we know. Now, because there's two ions in each of these solutions, we're going to end up making two graphs. One where we plot the absorbance versus the concentration of the cobalt ion in moles per liter. The other where we plot absorbance versus the concentration of the copper ion, also in moles per liter. So what you guys are going to do is, with the data you get from the experiment today, you're going to have a spreadsheet, make a graph like this. It's going to plot the points, and it will, and you tell it to give you the equation of the best fit straight line. It's going to give you an equation in this form, y equals mx plus b, which you should be familiar with. M is a slope, b is a y-intercept. It's going to give you something that looks like y equals some number, which is a slope, x, plus some number, which is the y-intercept. In this experiment, we're concerned with x. We want to find because x is the concentration of our unknown. So if you rearrange this equation a little bit, solve for x, you're going to know y. Y is the absorbance of your unknown. B is from your equation, the number that the spreadsheet gives you, the y-intercept, m is the slope. Plug in, and you're able to calculate the concentration of cobalt and also of copper in your unknown. To do that, okay, to make our standard curve and all that, we're going to need a stock solution. You should calculate ahead of time and place this in your pre-lab about how many grams of cobalt-2 chloride hexahydrate you'll need to make about 50 milliliters, well, actually 50.00 milliliters of a roughly 0.30 molar solution of the cobalt-2 chloride hexahydrate. You also should calculate ahead of time how much copper-2 sulfate pentahydrate you'll need to make a 0.12 molar solution, 50 mils of that. And you're going to weigh out, or have weighed out, roughly that amount. Make your stock solutions, which I'll show you guys in a few minutes, and then we're going to do some dilutions, which means, by the way, in your calculations section, you'll be using the dilution equation. Now, to make those dilutions, you're going to use a burette. We're going to use 25 milliliter burettes. Just to remind you how to read a burette. So the first thing about a burette is the top mark is 0. It's not the very top of the burette, but the top mark is 0. And the bottom mark, in this case, we're using 25 milliliter burette. So the bottom mark will be 25. Now, that 25 is not the bottom of the burette. There's some space after that. We don't ever want to go past this because we don't know how much we're adding past that. The next thing to know about the burette is that the closest marks are 1/10 of a milliliter apart, which means that when we read this burette, we record every measurement from it to 2 places past the decimal, the nearest 100th of a milliliter. And so we read it just like we do any other column with a liquid in it. We read the bottom of the meniscus. And so the way we use these guys is we put some of the solution, or we're going to use it for DI water also, into there, read the initial volume, add about how much we need, and read the final volume. Because we're going to read the initial and the final volumes, the actual amount that we add will be our final volume minus our initial volume. That's going to give us 2 places past the decimal. And also that means we don't have to be careful to add exactly 1 milliliter or 2 milliliters or what have you. But as long as we know the initial and final volumes, we're good. So let's say this was our initial volume. We would read the bottom of the meniscus and we would say, all right, this is between 1 and 2 milliliters. 1.1, 2, 3, 4. So it's going to be 1.4 something. So you have to estimate that. I might call that 1.43 milliliters. If you called it 1.44, 1.45, I wouldn't argue with it. That will be our initial volume. Then we're going to add how much we need, roughly, read our final volume, and record that. That's what goes in the data table. Then in your calculations, you do the subtractions and find how much was actually added. That's how we're going to do our dilutions. And that's pretty much what we're going to do. Why don't we go on over there and start the experiment? All right, guys, so the first thing we're going to need to do is to make up our stock solution. Remember, you figured out already about how many grams of the cobalt 2 nitrate hexahydrate you need and of the copper 2 sulfate pentahydrate. So I've weighed those out already. I'm going to take a 50 milliliter volumetric flask, glass funnel, and we're going to add, and actually it's easier this way. If you first add the copper 2 sulfate pentahydrate, it goes in pretty easily. Now there's still some copper 2 sulfate pentahydrate on there. We want to get as much of that off as we can. So we just take a little bit of DI water and rinse that down on into the volumetric flask. Once we get that in, then we add the cobalt 2 nitrate hexahydrate. The reason we add this second is it's kind of lumpy and hard to get through the funnel, so we need some water. But it'll go through. And we're going to also rinse off this whey boat, make sure we get all that in there. All right, now that we have 2 compounds in there, we're going to add some deionized water. A little more than halfway. Start dissolving this. Once we get everything dissolved, then we can fill it up to the line, get our meniscus just touching the bottom of that line. Now the cobalt 2 nitrate hexahydrate, it dissolves pretty easily. Copper 2 sulfate pentahydrate, it takes a little bit more. So at this point, we're going to have to let it, dissolve for a while, swirl a little bit. All right, guys, so now that we have everything dissolved, we're going to add water so that the bottom of the meniscus just touches the top of that line on the neck. This is the part we have to be careful about. If we go over, there's no taking it back out, and we have to remake the entire solution. There. Now that we have it filled up to the line, put the stopper in again, invert it. Now we have our stock solution. We're going to take the stock solution and come over to our burettes here. One of these burettes, I've already put some deionized water in it. And with these burettes, by the way, guys, there's almost always some air in the tips. So what you do is you fill it up with whatever you're going to put in it, and then empty the empty the solution or the water out until you get the air bubbles out of the tip. So that's good. I'm going to add some stock solution to this burette. The stopcock has to be closed, which is perpendicular. Otherwise, it'll just go right through. Pour it in, and I'm going to fill it up past the zero, up, past the top mark, and then we'll get the air bubbles out. There we go. That's pretty good. Drain a little bit, the air bubbles out. That's good. All right. So now I have my water, I have my stock solution. I'm going to write in my data table my initial volume of my stock, initial volume of my water. I have 5 small test tubes that I've labeled 1, 2, 3, 4, and 5. In test tube that's labeled number 1, I'm going to add about 1 milliliter of the stock and about 4 milliliters of the DI. Test tube 2, about 2 milliliters of stock, 3 of DI. Test tube 3, 3 of stock, 2 of DI, 4 of stock, 1 of DI, 5 of stock, 0 of DI for test tube 5. So again, it doesn't have to be exactly 1 milliliter. What we do is we read the initial volume, record it in our data table, figure out where 1 pass that is, add 1 to that number. Open up the stopcock till we get to about that place, close it. Doesn't have to be exact. Read the new volume, the final volume, 2 places past the decimal, record that in our data table. Test tube 2, whatever we're at now, we're going to add 2 to that number. Add till we get to about that, close the stopcock, read the new volume, and so on for 3, 4, and 5. Then we do the DI the same way. Test tube 1, we want about 4 mils of DI, so read our initial volume, add 4 to that, just get about there. Record our final volume here. That's test tube 1, and so on for test tubes 2, 3, 4, and 5. Now we're ready to come over here to the spectrometer and make our standard curve. All right, guys, so now we're ready to measure the absorbance of our stock solutions and as well as our unknown. First thing we're going to do is when we come up to the spectrometer, should be on the home menu, and the Spec 200E modern interface should be red. That's the one we use. So what we do is we press enter, which is this button right here. And now, okay, the first thing we have to do is find the Lambda Max, the wavelengths of maximum absorbance for both cobalt and copper. So we arrow over here until up here where it says live display. We want that to say scan. So scan, once it's there, we press enter. Now, before we can do anything, guys, what we have to do is we have to zero out the spectrometer. So what we do is we take an empty cuvette, some deionized water, fill the cuvette to that line, right about there. We always wipe off the cuvettes with a Chem wipe. Pop the cuvette into the spectrometer right there. Close the door. And there's a button right up here that says 0.00. That's a 0 button. Press it. And see where it says auto 0 right there? When that goes away, it's zeroed. And we're pretty much finished zeroing it for the experiment. So guys, now that it's zeroed, we take this out, dump out the water, and what we're going to do is we're going to find the Lambda Max, we're going to use our solution 5. That's the one that does not have any DI water in it. Now, there has some DI water droplets in here. That would dilute the solution, so what we do is we add a little bit of our solution 5 and then dump it out and then fill it up. That way, it won't dilute our solution. All right, guys, so we're going to add a little bit of solution 5 to the cuvette. Condition it, basically. Give it a little swirl. And now we're going to have a waste beaker here, guys. We cannot throw any of this solution down the drain. Both the cobalt and the copper are toxic, not good for the environment. So we dump this into our waste beaker, which Matt will have a waste container to put that in at the end of the experiment. Now we're ready to fill up our cuvette with solution 5. Just about that much is good. As always, we wipe off the outside with a Chem wipe. We're going to put it into the spectrometer now. So we open up the door, place it right here. Now we're ready to go. Just press enter, which is this arrow right here. And when we do, it's going to scan through 400 nanometers all the way through 900 nanometers, measuring the absorbance along the way. And it'll give us a graph. See how it says scanning down there? When that goes away, we'll see our graph. All right, see that graph right there, that red line? What that's showing us is it's the absorbance, and there's 2 peaks here, right? The one on the left, that's due to the cobalt ion. The one on the right, well, that's due to the copper ion. And what we need to find is which wavelength gives the maximum absorbance for each of those 2. So this gives us the wavelength up here, this gives the absorbance down here. So the first thing we're going to do is go to the cobalt ion. So that's this peak right here. See that green line right there? Wherever that's at, that's the wavelength and the absorbance that it's reading. So what we do is we use this button here, and it'll move with us until we get over onto this cobalt peak. We get roughly around the middle. Our goal is to maximize this number right here, the absorbance, but the number we record is the wavelength. So what we can do is 1.42, we're going to use the arrows, go 1 nanometer at a time, 1.43, 2, 1, and it looks like it's going down, so I think 1.43 is the maximum absorbance that we'll see. Let's just check both sides to make sure. Yeah. All right, so we're going to go to 1.43. But what we care about is the wavelength. So for me, 513 nanometers is the Lambda Max for the cobalt ion. We're going to write that down in our data table, and now we're going to do the same thing for the copper ion, which is this peak right here. So we turn this knob, get that green line somewhere around the max. Now with this one, I have a feeling we're going to see more than one wavelength that gives the maximum absorbance. We just kind of go to the middle one. So somewhere around there. I see 1.51, so I'm going to arrow over, see if I can get that any bigger. There's 2, 2 again, 2, 2, and it's going down. So let's see, I see 2 at 829, 52, again 823, again 820, so roughly 824 is in the middle somewhere. So why don't we call 824 our Lambda Max for the copper. I'm going to write that number down in our data table too. So 513 nanometers for cobalt, 824 for copper. Now what we do is we're going to go through, measure the absorbance at each of those wavelengths for cobalt and for copper. So we're going to take, we already have solution 5 in here, so we can just do that easily. If we go back to the home screen, just by pressing the home button, press enter for the Spec 200E modern interface, and see where it says live display right there? That's what we're going to use for the rest of the experiment. So if we press enter, that's the wavelength which we can adjust. And that absorbance there, that's 824, so we would write down that's solution 5. That's the absorbance for the copper ion. So we change the wavelength until it's 513. So 514, go down 1, give it a minute. And that absorbance there is the absorbance for solution 5 for cobalt. And all we do is we do the same thing for solutions 1, 2, 3, 4, and then the unknown. All right, guys, so now that we have the Lambda Max for cobalt, the Lambda Max for copper, the absorbance for solutions 1 through 5 for both cobalt and copper, as well as the absorbance for cobalt and copper of the unknown solution. We have all the data we need for the experiment. We're finished. That's all there is to it.